Hello, Math 201 students. Today we're looking at a lesson in optimization. How can calculus help us to make the best real-world decisions? In other words, optimizing a situation. I love this topic. I really enjoy it. Maybe as we get into it, I'll be able to explain why. I'm not really sure if I can explain why I like this a lot, but we'll see. All right, so here's just an example. One thing has to do, I can say this, it has to do with real world stuff, real world examples. So, of course, that means word problems, which may scare some of us, but it shouldn't. Word problems are what makes math worth anything in life. All right, so first example, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What dimensions for the field should the farmer choose to have a field of maximum area? All right, this is why I like this stuff. It's trying to make the mathematically optimum decision based on a given set of conditions, which is what we're all trying to do every day. I mean, that is what life is. It's making the best decision based on the reality of situations. I love that. It's about truth, using truth to make decisions. So, what are the dimensions of this field? So he's got a certain amount of fence, and he's trying to make a perimeter around this rectangle, but he's wanting the rectangle to have a maximum amount of area for that given amount of fence. You know, if the fence had no limits, he would just make an infinity by infinity rectangle and have an infinitely large area. But there's this condition. It's a limited amount of fence. So here's what I like to do. First, I like to introduce variables. And it's always good to, if you can draw a picture of the situation. I don't know if you can see this. It may not be big enough to see. Let me see if I can blow that up some. So this is a kind of a sketch that you could do of the situation. Here's the river, and here is a rectangular shape bordering that river. And the fence itself will only be these three sides because the river itself forms the fourth side, so there's no need to have fence there. So it's just these three sides that are going to make up our rectangle. So I base the variables. What should the variables be? I think the variables should be usually based on what the problem is asking you to find. So what's the thing actually asking us? What dimensions for the field should he choose? So that should be the variables. The variables should be the dimensions of the field. In other words, what are the dimensions of a rectangle? Usually we call it length and width. So I'm going to have a variable that's called L and another variable that's called W. All right, what is it also asking me to do in terms of those dimensions? It's asking me to maximize the area in terms of those variables. All right, what do we want to maximize? The area. The area of what? The area of a rectangle. So you're going to make an equation based on that optimization problem. The area of a rectangle. A equals my variables, which are length times width. All right. Now, this is going to be the trick of the trade here. This is what's going to separate your success from failure in being able to do this problem by yourself at some point. Are there any other considerations for the variables besides just that length times width equals area? Or in other words, is there another equation that we can make to relate the length and the width? Because we don't want to have to maximize something in terms of two variables. It's kind of like solving an equation with two variables. You can't do that. If you can get one variable in terms of the other, then you can do it. So in fact, there is another condition, another consideration that can give us an equation, and that is the fact that we only have 2,400 feet of fence. So what does that mean? How can we make an equation out of that? So that means that the three sides of the rectangle that we said earlier in this picture, those three sides have to add up to that 2,400 feet. So we can just make that into an equation. The width plus the length plus the width again equals 2,400. you can simplify that down to just 2w plus L equals 2400. So now you can use substitution. You can write one of these variables in terms of the other, solve for either w or L, and substitute it into the area equation for the other variable. All right, I think the way that I would probably do that is I would move the 2w over and say that L equals 2400 minus 2w, which is what I have written right here. So substitute 2400 minus 2w, substitute that in for L in the other equation. Substitute this expression, which is equal to L, substitute that into, oh, not that one. Substitute that into the other equation in the place of L. So now A equals length, which I'm just going to call 2400 minus 2w times the width, which is just w again. Simplify that, and we have area as a function of the width is equal to 2400w minus 2w squared. That is my area function as a function of just one variable, just the width. So we can use, so what we can do is we can do this a couple of different ways. One, we can use something that we already know before. We knew this before calculus. We can just graph this function and find the maximum. You know, it's going to make a parabola. If we find the maximum, that'll give us the value for w. That will give us the maximum area. All right, but we can also do this now with calculus without even looking at a graph, because we know that when we have a maximum, what is true about, as far as calculus is concerned, what's true about the equation? What's true about the function? Its derivative equals 0 there, because the slope is 0 at a maximum or a minimum. So we find a prime of w is equal to the derivative of this, 2400 minus 4w, and we set that equal to 0. And then we solve for w, move the 2400 over, or maybe I just move the 4w over. 2400 equals 4w divided by 4. W equals 600. So the width is going to be 600, and then plug that width back in for here. Plug it into there to find the length. The length is going to be 2400 minus 2 times 600. So that's 2400 minus 1200, which is 1200. So the width is 600 and the length is 1200, and those are the dimensions that will maximize the area based on the conditions that we're required to meet. So we have just optimized this situation. And we could even go one step further and say that the maximum area, let me say this, a maximum area of what? What will be the maximum area? Well, I plug 1200 for the length, 600 for the width, and let's see if I can do that in my head. We got a 0, a 0, a 0, a 0. 6 times 2 is 12, carry 1, 72, 720,000. I hope I did that right. I think I did. 720,000. What? 720,000 what? What are our dimensions? Feet, right? So square feet can be achieved by creating a 1200 by 600 rectangle. 1200 for the length, 600 for the width. And that, I like to finish my problem off with a summary statement that tells about everything we did in that problem and answers the question. I think that finishes up example 1 for us. And here you can see the steps again written here. I did go into a little bit more detail in this written explanation here. When we found that W equals 600 as it was one of our critical points, I kind of already knew that this was going to be a maximum. Well, based on the problem, it's fine, the maximum, but also based on the fact that this is the graph of a parabola that opens downward because of that negative in front of the W squared term. But you can also verify that with calculus by checking the second derivative. If you do the second derivative, you do a double prime. A double prime would be just the derivative of a prime, which would just be -4. And so that's negative, which means that it's concave down, which means concave down means that what we just found was a maximum, not a minimum. All right. Yeah. So let's see this substitute. Yep, we did everything else that we said in the rest of the explanation. Here's a graph of what we just found. You can see this is a graph of the area based on the length of the rectangle. You can see that if the length is 0, we have an area of 0. If the length is all the way out, no, I'm sorry, maybe this is the width. Based on the width of the rectangle, I'm sorry. If the width is 0, the area is 0. If the width is 1200, then you would have 1200 and 1200. There would be nothing left for the width. Sorry, nothing left for the length, which would mean it would be no length, which would mean it would be a straight line instead of a rectangle, which would have no area also. But you can see that as it goes beyond 0, the area increases and increases and increases and increases. But then once it gets past a certain point, the area begins to decrease, and we just found that optimum point where it reaches its highest value. Our second example, a company wants to manufacture a cylindrical can to hold 1 liter of oil in such a way as to minimize the cost and the waste. What should be the dimensions of the can in order to minimize the cost of material? So we have a condition. We have to hold a certain amount of volume in this shape, but we want to make this cylindrical shape to be the smallest it can be, yet still hold that 1 liter of oil. What do I mean by small? What do I want to be small? I can't make the volume any smaller than the condition says, but there are lots of different ways to hold a liter. You can have a really wide and short cylinder, or you can have a really tall and skinny cylinder, or somewhere in between. And the question is, which one of those designs would minimize the cost? Another way to say that is, which one of those designs would use the least amount of material? Okay. So when I'm talking about using an amount of material, what I'm talking about is a surface area, the area of the material. And it's the area of the material on the surface of that shape. It's called a surface area. The surface area of this shape is what I'm trying to minimize. I have a surface area here and surface area here and surface area on the bottom, and I'm trying to minimize all of that in order to minimize the amount of material I have to use, which would minimize the cost and minimize the waste when that thing is thrown away. So you can see this is a worthwhile endeavor to see if we can do this. We're going to meet our needs in the most efficient way possible. All right, so what do I like to do? I like to introduce variables, and I like to sketch this thing. So I'm trying to find the dimensions, right? The dimensions of the can. Well, when I have a cylinder, what are the relevant dimensions when dealing with a cylinder? I'm trying to blow up this drawing for you. You have this cylinder, and we have that cylinder has a height, and it also has a diameter, or you could say a radius. The height and the diameter or radius define that whole sphere, the volume and the surface area of that sphere. All right. So we can see in this written explanation that I have here that we are trying to minimize the amount of surface area for the cylinder. So let's think about a cylinder. I may need to get a better way to draw. Now you have to kind of use some visualization, some imagination perhaps, and say, what are we dealing with when we're dealing with a cylinder? What do we have on top? We have a circle. So we're going to have the area of a circle. The total surface area is the area of the top circle What do we have on the bottom of the sphere? Another circle. So plus the area of the bottom circle. But what about this whole middle part? What in the world is this middle part? Can you visualize? Can you come up with it? Maybe pause it before I give it away. Think about if you were to kind of think about it being open at the top and bottom. And if you were to kind of cut this thing right here and then unfold it. Okay, imagine unfolding it. Unfold that thing. What do we have when we completely unravel that cylinder? What we have when we unravel it is a rectangle. Can you visualize that? It's almost like a scroll. If you unscroll the scroll, you have yourself a flat rectangular page. So this plus the middle. I forgot to say area. Plus the area of the middle. What? Rectangle. So I have three shapes that make up the total materials that go into making the cylinder. All right, now we have a radius of that circle and we have the height of that cylinder. Hopefully we can get all three of these in terms of just those variables. Well, what is the area of the top circle? The area of the top circle is pi r squared. And the area of the bottom circle is also pi r squared. What about the area of the rectangle here? Well, hopefully you can see that this dimension of this rectangle is the same thing as the height of that cylinder. But what about the length of this rectangle? What is that? What does that have to do with R or H or anything? As we unravel this cylinder, this circle is what is unraveling. So that, maybe you can see this already. The length of this rectangle is the perimeter or the circumference of this circle unraveled. It's the circumference of this circle as it is stretched and spread out from its circular shape. So this is the circumference of the circle. What's the circumference of a circle? It is 2 pi r. That basically is the length of that rectangle. And we know that the total area of that rectangle is the length times the width. Well, In this case, the width is, if I call the 2 pi r the length, the width here is we call that the height, or the h of the cylinder. So times h, which is the height or width of that rectangle. Let me simplify just a tad bit. So surface area equals 2 pi r squared plus 2 pi r h. We are trying to maximize that. The problem is we have two variables here. We have r and we have h. And so we're going to have to do something to get rid of one of those variables, to substitute one of those variables. So what other condition is there that can give us another equation that relates the radius and the height? It is that volume condition. What did it say about the volume? It said that the volume needs to equal 1 liter. What is the volume of the cylinder? What's the formula for the volume of a cylinder? The formula for the volume of any prism or any geometric solid where you have a face, the front face of this solid that is then extended out in a parallel way, is always going to be the area of the face times the length of the extension of that face. So, if you had like a triangle that was extended like this and forming a prism, sorry about my drawing skills, then it would be the area of that triangle times that length of that extension. If you had a rectangular prism where you had this thing, then it would be the area of the face of that prism times that extension. Well, what we have in a cylinder is the face is a circle. So the area of the face is the area of the circle, the top circle or the bottom circle, either one, which is pi r squared, times the length of that extension is the height of that cylinder. If you want to call it height or if you want to call it length, it doesn't matter. Since we've already called it height elsewhere, let's call it height here. And we have said that that volume needs to equal 1. And so I'm going to solve for either r or h in terms of the other variable by getting one of these things by itself. I think I'll probably rather just get h by itself. So h equals 1 over pi r squared. So I'm going to substitute this in for h here. So now my surface area is equal to 2 pi r squared plus 2 pi r times 1 over pi r squared. And I can simplify that because the r squared, that r squared can reduce with that r. The r goes away and that r squared becomes an r. So the surface area is 2 pi r squared plus, the pi's can cancel as well. So plus 2 over r. And this is what I'm maximizing, and that's the simplest way we can write it in terms of one variable. And so I believe I will, again, you could find the, you could graph this thing and find the maximum, or actually we'd be finding the minimum, wouldn't we? We'd be finding the minimum of that, or we could, a graphing calculator could come in handy there, or we could just use our derivative techniques to find that minimum. We can do the derivative of the surface area which is going to be 4 pi r. And if I kind of rewrite that or think about that as 2r to the negative 1, then it's going to be minus 2r to the negative 2. Or I could rewrite that as 4 pi r minus 2 over r squared. And I've got to set that equal to 0. I'm finding where the derivative equals 0 to find where the minimum is, because at the minimum, the slope of the tangent line is 0. That's what I'm doing. I'm finding that where that derivative equals 0 to find the extrema of the function. So let me move my 2r squared over, and I've got 4 pi r equals 2 over r squared. I think I could just cross multiply here and cross multiply and get 4 pi r cubed equals 2. So r cubed equals 2 over 4 pi, which reduces to 1 over 2 pi. Right? 2 over 4 just reduces to 1 over 2. Take the cube root of both sides. And r equals 1 over the cube root of 2 pi. Because the cube root of 1 is 1, and the cube root of 2 pi, I'm just leaving it like that. All right, at this point, I am thinking this is a bit of a strange answer for the radius, and it just dawns on me now that what did we do for our volume? For our volume, we put 1. 1 what? 1 liter. But then we've got variables over here that are not volume liter units, but are length units. So I should have done that over here. I should have said, instead of 1 equals pi r squared h, and this is kind of a diabolical trick that you run into sometimes with units in these problems, and it really happens in the real world too. Instead of putting 1 liter, I'm going to put 1 liter is 1,000 cubic centimeters. So I'm going to put 1,000 equals pi r squared h. Now the units are consistent. This is cubic centimeters, and this is cubic centimeters as well. So now instead of h being 1 over pi r squared, h would be 1,000 over pi r squared. And then that would have gone into there. So it would have been, what would that have changed? That means that this would have been 1,000, which means that this would have been 2,000 in this step, and this would have also been 2,000 r to the negative 2. And this would have been 2,000. And this would have been 2,000. So I'm going to start over at this step here. So now it'll be 2,000 over 2,000. It'll be 2,000 equals 4 pi r cubed. Now divide by 4 pi. That will reduce to, if you divide them both by 4, that would become 500. And this would cancel out. So that r cubed equals now 500 over pi cube root both sides. So now r equals the cube root of 500 over pi, whatever that is, and that's in centimeters. So I could get that as a decimal. If my little phone calculator just did this right, that would be around 5.42 centimeters. And so now I know r. And so I can use r to find h, probably best in this equation over here. So 1,000 over pi times the cube root of 500 over pi squared. If I do that, let's see here. $1,000 divided by pi divided by parentheses 500 over pi close parentheses raised to the 2/3 power. I get, this is the exact value of h, but as a decimal, it would round to just about 10.84 centimeters. So now we have our dimensions for the radius and the height. My surface area is what I was trying to minimize. I probably do need to do the second derivative just to be thorough and make sure this is a minimum and not a maximum. So I want the second derivative to be positive at this value of r so that it would be concave up. That means it would be like that, so that the point we just found we would know would be a minimum. But the derivative of this is going to be 4 pi plus 4,000 r to the -3. Or we could say 4 pi plus 4,000 over r cubed. And this, no matter what value we put in for r would always be positive. So no matter what positive value we put in for r, this is always positive, which means we do have concave up the whole time. And so we do know that our value that we found for r produces a minimum for that surface area. So let me finish up by writing a summary statement. That means that my surface area is going to be 2 times pi times, what was r again? The cube root of 500 over pi. The cube root of 500 over pi squared plus 2,000 over the cube root of 500 over pi. That was just me using this equation right here and plugging in that value for r. So let me compute that. 2 times pi times 500 over pi, close parentheses, to the open parentheses 2/3, close parentheses, power, plus 2,000 divided by parentheses 500 divided by pi, close parentheses, raised to the open parentheses 1 divided by 3, 1/3 power. And that gives me that the surface area, if I did this correctly in my little phone calculator, is about 553.58. What is that? Square centimeters. And let me summarize this now. A minimum surface area. Let me say this: cost can be minimized by achieving a minimum surface area of 553.58 square centimeters using dimensions of r equals the cube root of 500 over pi, which is about, what was that, 5.42, something like that. and h equals, what was h? 1,000 over the cube, 1,000 over 500 over squared, or around 10 point, what was it? 10.84. Huh, that's interesting. I'm noticing that the height is exactly twice the radius. So producing a cylinder whose height is double its radius minimizes the surface area of that cylinder. And I think we just observed that to be true. So that statement summarizes everything that we figured out in that problem. So again, looking at the presentation that I created earlier, going through the words, you can feel free to pause this if you want to go through these words and read the explanations as given in a systematic way through this presentation. And I believe that is the last slide for that. Well, no, it's not. There's one more. Because it shows a graph of that surface area function, and it shows you that you have a minimum right there. 5.42 radius, 553.58 surface area. Third example. A man must get from point A on one side of a 3-kilometer wide river to point B on the other side, 8 kilometers downstream, as quickly as possible. He can do so by doing any combination of rowing his boat or running along the shoreline. He can row his boat 6 kilometers per hour and he can run 8 kilometers per hour. How far downstream should he land his boat before he starts running down the shoreline? So a picture would be very helpful here. Here is the situation that we have. We have this river. Okay, let me blow this up a tad bit. We have this man. He's right here. He starts out right here. He's got to get to here. So he can either run or row his boat or do some combination of those. Like he could just row his boat straight across there, or he could run straight across here. Row his boat straight across to the other side and then run all the way like that. Or he could kind of do a little combination of that by rowing some distance and then running some distance. So that's going to be a pretty cool problem, I do believe. The thing is he runs a little bit faster than he can row. If he rowed just as fast or faster than he could run, then it would be obvious that the answer would be just to row straight to there, because that's the shortest distance. But the fact that he can run a little faster than he can row means that perhaps he should run. He shouldn't spend all of the distance rowing. He should do some of it running, because he does that faster. So that might decrease the total time. And I think that's the goal here, if I can read that problem again. How far downstream should he land his boat before he starts running down the shoreline? Because he wants to get there in the quickest way possible, I'm assuming. Yeah, it says that. Get downstream as quickly as possible. So we want to minimize the amount of time it takes. All right. So the total time is going to equal his time rowing plus his time running. And we know from physical science that speed equals distance over time, or if we solve that for time, we could say speed times time equals distance, or we could say time equals distance over speed. So that I can now say that time, the total time, is equal to the time rowing, which is going to be the distance rowing, divided by the speed rowing, plus the time running is going to be the distance running divided by the speed running. Pardon my terrible handwriting. I think you get the picture. So if I can draw my picture now, that little line right there represents the distance that he rows, which we will call D1. This distance right here is going to represent the distance that he runs, and we're going to call that D2. So now we can say that our total time is this right here. That it's going to be D1 divided by his speed rowing plus D2 divided by his speed running, which simplifies into D1 over 6 plus D2 over 8, because 6 is the speed that he rows and 8 is the speed that he runs. Okay, so again, we have two variables. We want to minimize this time, and we have two variables, so it would be very helpful, if not even necessary, probably necessary, to get one of those variables in terms of the other. So let's spend a little thought energy on that. All right, look. You can see in this picture, we want to be able to relate this distance to this distance somehow. And some things that I know based on looking back at the problem, it says that the river is 3 kilometers wide, a 3 kilometer wide river, and it also says that point B is 8 kilometers downstream from point A. Let me fill that information in. The river is 3 kilometers wide. And point B is 8 kilometers downstream or downriver from point A. So maybe I can use that to help me find an equation to relate D1 and D2. I'm thinking about using this right triangle right here. Thinking about using that right triangle right there. Let's think about that. We already know one side of that right triangle. We already have a variable for the hypotenuse of that right triangle. What about this side right here? It is not 8 kilometers, and it is also not D2, but it is the difference between 8 and D2. This is 8 kilometers, take away D2 from 8. So it's 8 minus D2. So now I can say, Pythagorean Theorem, that thing, 3 squared plus 8 minus D2 squared equals D1 squared. Yes, sir. We are on our way. So 9 plus 64 minus 16 D2 plus D2 squared equals D1 squared. I just did some distributing there in my head to get that. 9 plus 64 is 73. 73. Let me rewrite this a little bit better. I think I want to write it like this. That's going to be D1 equals the square root of D2 squared minus 16 D2 plus 73. Hopefully you see how I got that. I square rooted both sides to get D1 by itself. And I combined the 64 and the 9, and I just rearranged this thing so that the highest exponent term comes first. So that's going to be very helpful. Now I can substitute this expression for D1 right there. So now my total time is equal to the square root of D2 squared minus 16 D2 plus 73 over 6 plus D2 over 8. Now I would need to minimize this by finding T prime, and T prime is going to be sort of difficult. I think a little bit difficult, not impossible, but it would be a little difficult. So I mean, if we had to do it, we could do it. Like we would just, I think we would write just to prove to you that we could do it. I think I'd rewrite this. Rewrite T as 1/6 times D2 minus 16 D2 plus 73 to the 1/2 plus 1/8 D2, and I would do the power rule to do the derivative by moving the 1/2 down here and subtracting that by 1, and also doing the chain rule, which would mean I have to do the derivative of what is in there as well, and do the derivative of that term and all that good stuff. And we could do it. Just trust me, we could do it. But I think if I were you and I could use my calculator, I believe what I would do is I would graph this function in my calculator. And I would find where that thing is at a minimum. Here's some work I did. I did a little bit different than what I showed you by hand, but as I've explained this in this presentation, I made what I did here was I let D1 be, I let this thing be a variable X instead of calling it 8 minus D2, and then anyway, you can see what I did, and then I did some work to get the derivative and set it equal to 0, and I found that the answer was plus or minus 9 over square root of 7, which comes out to be about 3.4 kilometers. And that was solving for x being neither answer, but 8 minus that gives me D2. So the D2 is about 4.6. So I should run about 4.6 miles and plug that back in for D1, and D1 is about 4.53. So I should row about 4.53 kilometers, and I should run 4.6 kilometers. And 3.4 kilometers is how far downstream I should go right here. How far I should land my boat in order to row that far and run that far. But again, I think if I were you, I would use my calculator and graph it. And this shows you a picture of the graph. You're probably going to want your window to be something along the lines of what my window is. Like x goes from 0 to 8, y goes from 0 to 1.7 or so. And you can see that the minimum is that. Now your minimum would be a little bit different than that, because your minimum is not based on x, it's based on d2, which has to do with x, but it's not exactly what x is. So that is the end of the problem. Now, I realize that there are some difficult concepts, some difficult steps, some high horsepower thinking that has to go on here to accomplish these problems, but that's kind of what it's about, man. That's what gets you to a higher level of mathematical rigor and ability. So do the very best you can. Try to do these by yourself. If you struggle with these, we can answer some questions in class. I may also try to make another video where I go through some of the homework problems, but this gives you an idea of what to do, how to do those homework problems. Good luck to you on completing that. See you next time.